Okay, so we have the skateboarder problem. First of all, let's remind ourselves of the kinematics equations in the horizontal and vertical directions, X and Y directions, because we're going to be applying those in lessons 2 and 3 here. So you should have these already written down somewhere. So delta X. This is finding a displacement delta X when all of these other guys are known, the initial velocity, final velocity, time. This is finding displacement when you know initial velocity, time, and acceleration. Final velocity when you know initial, acceleration, and time. And this is finding final velocity when you know initial velocity, acceleration, and displacement. I should have written that a little smaller, but anyway, on the right-hand side, that's the X direction, and now the Y direction. Same thing, couple of changes. We change from X to Y. And that'll be in lesson 3, VIT. And then A becomes minus G, so this becomes negative 1/2 GT squared. This is VI minus GT. 2G delta Y. So that's what we'll be working with in lessons 2 for X direction. And okay, and lesson 3 Y direction. Okay, so now first we're going to do in the X direction. So skateboarder problem. So keeping those in mind. So as with any physics problem, the way I like to do things, you can do this or a version of it. Draw the picture when needed. You know, make a habit of that. Write down the given information. Pick the equation that's going to relate to the given information and solve for the unknown. So this is basically what we're doing right here for these few questions in the beginning, is we write down a bunch of information and then let's use the best equation. A skateboarder, so obviously on the x-axis, he's horizontal, you know, you're kind of vertical with, you know, going up a little tube or something, but for the most part, horizontal. A skateboarder is moving at a constant speed of 1.75 meters per second. When she starts up an incline, that causes her to slow down with a constant acceleration of negative 0.2 meters per second squared. How much time passes from when she begins to slow down until she begins to move back down the incline? Okay, so we got to figure out how much time it takes for her to slow down to get to the top. So the implication here, and it's kind of weirdly worded, sort of the whole thing with constant velocity. Obviously, there is a deceleration here. So if that speed is not going to remain constant, what do you think the speed is going to be at the end or at the top of her slow down point, or let's say her maximum height? What do you think the speed should be? She's slowing down at this rate. So what should be that speed at the top? What do you think? When things slow down, what's the object? What are you trying to do when you put your foot on the brake? Put your foot on the brake. What are you trying to do? You're trying to come to a
stop.
Yeah. So you're trying to come to a stop. That's the point of, you know, brakes. You want to slow down and stop at the red light at the stop sign or home. So the final speed at the top, when she begins to slow down, sometimes the dissection of a problem gets rather annoying because of how they worded it. Because anyway, but we do what we do. She slows down to a stop, so her final speed is going to be 0. So this is an initial speed. So again, the object is that she's going to slow down at some point. And we're just going to take it from this perspective that at the top of when she slows down, from when she slows down until she begins to move back. So at that top, at that point, the velocity is going to be 0. So again, it's a little, you know, it's a little weird. So she's cruising along at 1.75 meters per second.
Mr. Kelly.
Yeah.
So is this assuming that so she immediately starts off at 1.75 meters per second? How come her initial velocity isn't 0?
Well, this is like a snapshot. So whatever she was doing before this is immaterial. So somebody started recording information at this moment when she was going at 1.75 meters per second.
Oh, I see. I see.
Yes, perspective. Like you can take it from the beginning at 0. You can take it when she's going at constant speed. You can take it someplace else. Yeah. And so she goes up this incline, and okay, so at the top here of the incline, final speed 0, and she gets to be 0 at this constant deceleration rate. We know that, let's say, for example, she starts off large speed and then gets smaller, smaller, and smaller until 0. It goes from VI to V final equals 0, and the acceleration is the opposite. So friction in the sidewalk, the ramp, is causing her to slow down. And this deceleration or negative acceleration is at this rate. So we got all that information and we can find our time. Which of these 4 equations in the x-axis would be most appropriate to find time?
Would it be VF equals VI plus AT because we have everything except the T?
Yes, that's perfect. So we have the VI, we have acceleration, we have VF, which is that stop. You can solve for T. Excellent. So again, it's like, you know, information, picture to kind of visualize, maybe a motion diagram. You don't have to. It's just everything you need to internalize. Okay, this is the best approach. And the third equation is good. So VF equals VI plus AT. I'm solving for T. Now, once I got all that physics out of the way in place, I can put my algebra, my math, and solve for T. So this goes away because that's 0. And then I subtract both sides, AT, and then T equals negative VI. And this is negative because time is going to be positive. And that will be negative 1.75 over negative 0.2. There's your answer there. So tell me what you get. So what we're going to do, get this answer, a couple more, and then I'll have you break out into do this challenge question and another question. But okay, so 1.75 times 0.2 divided by 0.2, 8.75 seconds. It takes her roughly about 9 seconds to travel this distance and get to her final destination before she comes back the other way. And let's assume that the acceleration, the positive acceleration will be the same. Nothing's changed, still the surface between the friction between the tires, the surface between the tires and the road, that interface doesn't change because it's still the same thing. And she comes back the same way and achieves 1.75 meters per second going the other way. But yeah, that's, proper assumption. 8.75 seconds is your answer. That's how much time it takes her from when she begins to slow down to the point when she goes back down the incline. Kind of awkwardly worded there, but that's the point. Any questions from that? So it's like, these kinematics equations, these motion equations, kinematics, dynamic motion. Write down what you know, maybe draw a picture to help you see, and use the right equation. Number 2, a race car travels on a straight racetrack with a forward velocity of 44 meters per second and slows at a constant rate to a velocity of 22 meters per second over 11 seconds. How far does it move? Okay, and even number 1 here, we can figure out how far she travels, because now we have time, we have initial velocity, we have acceleration, deceleration, and we can solve for delta x by using the second guy, because if I want to find delta x, I got my initial velocity, I just solved for my time, I got my acceleration, I can use that one. Or I can use this one. I can even use this one for number 1. So it just depends what you got. Okay, so it's going along, cruising along, VI 44, and then eventually, it comes to a gap, and he's going slower. So V final. And the time period to do that, 11 seconds. Again, your picture doesn't have to be this, just anything to help you see what's going on. And then figure out how much time she is traveling, or time, but how far does she travel? Looks like that first equation up there would be useful, because I want to find delta x. I know my initial velocity, I know my final, I know time. So 1/2 44 plus 11 times 11. 22. Wow. Everybody hear about the 1111? I've been maybe it's power of suggestion, but people are saying, I've been seeing 1111s all over the place. And so have I. And to the point where Freudian slipped another 11 in there, but it doesn't mean anything. Anyway, if you've heard about that. Okay, so 1/2 of 66 is 33. 33 times 11, 363 meters. You guys get that?
Yes.
All right. Yes. Perfect. Yeah. Yeah, that's it. So that's really what you want to do for these guys. You want to just figure out what you know in the problem, write down the given information, and then write down the unknown. So for the unknown, using the appropriate equation. Okay, let's do one more before we. Okay, I'm gonna do number 3, but if you're on the textbook, or the online book, I'm gonna have you guys be prepared to do number 5 of that section. And let me see. And then if you scroll down on page 34, or basically the physical textbook will be page 73. I'm gonna have you do a couple of these guys. Right. So page 71, be prepared. We're gonna do one more example. Page 71, number 5, and page 73, number 5. And then online book people, it's the same page. You just have to scroll down, scroll around.
Mr. Kelly,
Yeah.
for page 71,
Mhm.
there's no number 5. There's 23, 24, 25, 26, 27. It's the same questions, but which question do you want us to do?
Oh my goodness, they renumbered them. Okay, so whatever the number is on page 71, I want you to do the challenge question with the car, the picture of the car.
Yeah, that's fair.
Okay. Yeah, so that's the one you're going to do. And then the next one will be, it's another challenge question. Starts off with Sakazi. Sakazi is learning to ride a bike, training wheels. So yeah, those 2 questions. Okay. Let's go back to number 3 of 71. Okay, so we have a car accelerates at a constant rate from 15 meters per second to 25 meters per second. So they're telling you what you should already know now. Hopefully we have some familiarity that acceleration involves changing speed, changing it from low to high or high to low. And changes speeds from 15 meters per second to 25 meters per second while it travels a distance of 125 meters. How long does it take to achieve the final speed? Okay, so we have initial velocity of 15 meters per second. The final is distance displacement, 125 meters. You know, and they interchange the word distance and displacement. I would say they're using distance because they're not indicating an actual direction. So distance is just a number, but we know that displacement would be the number and direction. So technically, if they said east, while it travels a displacement of 125 meters east, that would be the correct use of that word. And so now we want to find how long it takes to achieve the speed. So looks like we can use the same question or same equation as we did in the above question. So, okay, so let's multiply both sides by 2, get rid of the 1/2. Because we want to find time. And so now we can just divide by VI and VF. It's always good to get your expressions first. Don't put any numbers in there before you're ready. Now you got your final expression for the variable you wish to solve for. Put in your numbers now. 2 times 125 meters, 15 plus 25 meters per second. Okay, so that's going to be 250 divided by 40. So 6.25 seconds. That's how long it took for the car to go from 15 to 25 meters per second. You guys get that? Hopefully, any questions?
Mr. Kelly,
Yeah.
for the book, for number 73, you also want us to do the challenge, right? Because
Yes.
okay, because the numbering is not okay, yeah. So the challenge for
Yeah.
173?
Yeah, the same challenge. So under practice problems, that challenge, both of those challenges.
Okay.
That's weird. They give different numbers. Okay. Because then the bit after that is like problems 1 through 9. Check your progress or whatever the numbers are. Do you see that?
Yeah.
Okay. All right. Now, there is no example for the challenge, but yeah, I think we'll do that challenge. We'll do the page 73 one together because it's areas under a curve. So instead of on page 73, or we're going to do the problem before that challenge, before the Sakazi problem. So do what I see as number 4, but whatever the one before Sakazi. Okay, and it starts off saying Sunni. Okay, let me rewrite. Write that. So page 71 will be car in figure 16 problem, and then page 75, the Sunni problem. Okay, I'll give you guys 15 minutes to do that, and we'll come back, talk about that, and do the Sakazi problem. Okay. Okay, we're doing car in figure 16, but I want to do the area under curve one. The one we didn't do, which is the Sakazi problem, because we need to see how that works, because we're going to be using that for our project in some capacity. Okay, let me share this screen. I guess before I do that, what did just give me a volunteer? What was your answer for the car in figure 16 problem? What did you get? What was your speed? Anybody get that one? Any groups?
I got 17 meters per second.
17. Anybody else?
I got 18.5.
Anyone else? Any other groups? Let's speak on it.
I know I did mine wrong, but I had two. I did it twice, so I got 2 answers, but I got 0.19 or 0.75.
0.75.
Yeah.
Okay. Yeah. So we have a wide range of answers there. Okay. So I just want to see a few selections. Let's take a look at that one first before we go to the graph problem. Because graphs are data analysis. It's very important. I can literally teach physics from data analysis point of view. Data that drives our equations and analyses and observations, results, all that. Okay, so let's go to the car in figure 16. It travels west with a forward acceleration of 0.22 meters per second squared. Now, going west is generally considered the, wow, generally considered the negative direction or negative numbers. Okay. So negative 0.22 meters per second squared. What was the car's velocity VI at point XI if it travels a distance of 350 meters in 18.4 seconds? Okay, so we have acceleration, we have a direction, it's going west, we have a displacement, and we have time. So we're trying to figure out the car's initial velocity VI. Is there an equation that we can use, like, you know, something right off the bat that we can use to find VI? One of those 4 equations? Looking up top. You always are, with these type of problems, you have to write down what you know and then pick the one equation that's going to solve for the unknown thing, which is VI. Which equation works the best?
The second one?
The second one looks pretty good. Yeah, same equation as before. I don't know what that one was. Okay, but yeah, the second equation looks viable. So we have a total distance displacement to the west of 350. So that's going to be important too, because that's a negative number too, negative 350. You know, so let us be careful on that as well. Okay, so delta x EIT plus a half AT squared. Now this delta x is final minus initial, because any deltas are final minus initial. But if we were to write it in this fashion, we have 2 unknowns. We have a VI and an XI. So we don't need to write it this way. We don't need to worry about it in this form because we know that the total delta x is 350. We can then, after we find VI, we could find XI if we wanted to, but it's kind of, this would lead us down a wrong path here. We don't want to use this here. We don't want to use this form. So so let's see, delta x. So use that, and we want to find the VI. So so what we have is delta x. We want to subtract 1/2 AT squared because we're trying to isolate this guy. As any good algebra problem, we're trying to put everything else on the other side and leave the unknown on 1. So that becomes delta x minus 1/2 AT squared divided by t equals VI. Now remember, the delta x is also traveling. If it travels, so it travels west. That acceleration is also west because it said forward. So it's negative 0.22. Traveling west, the distance is negative 350. So we have negative 350 meters minus 0.5, that's 1/2, times negative 0.22 times 18.4 squared. Divide that by 18.4. Okay. Let's get this this stuff here first. So 18.4 squared times negative 0.22 times 0.5. That's going to give us positive 37.2 because these 2 negatives So we have negative 350 plus 37.2 divided by 18.4. And we divide that by 18.4. And we get negative 17. So who got that? Is this Miles, Rita, who said that? So whoever got negative 17 meters per second, that's it. We use our stuff efficiently, seemingly there, because we have to be sure that we consider those directions. That west doesn't just mean it's not arbitrarily thrown in there. West means something. It's a negative direction, or negative numbers mean going towards the west if we're horizontal, and then south if we're vertical. Questions?
Can you scroll up a bit?
I'm sorry.
Can you scroll up a bit, please?
I don't know why the mic is not working after the breakout. Let me put my headphones on. I think the sake of time, come back to the other challenge, the Sakazi. I want to do some free fall problems. So we want to go to next page, lesson 3, free fall. Okay, so we have two objects drop from the same height. They're going to hit the ground at the same time. They're going to have the same speed because gravity is going to accelerate them equally. We have the acceleration due to gravity, which is 9.8 meters per second squared. So we're now going to transform those A terms in those motion equations we were doing into the acceleration due to gravity that is on the Earth, which is negative 9.81 meters per second squared. Doesn't matter what masses you have dropping from the same height in a vacuum. This is what this works. This number is going to be calculated accurately in a vacuum situation where we have a feather, we have a hammer, drop from the same height, they're going to hit the ground same time. There is no air resistance, and the acceleration of gravity on the Earth is negative 9.81 meters per second squared. So that's our transformation in the equations. So let's use that transformation and also the fact that we are in the vertical direction. We're going to change our delta x's to delta y's. Let's start just doing a few of these guys.
Mr. Kelly, what number is this question?
Okay, I haven't gotten to a question yet, but I'm going to, all right, so I'll just answer you. Page 78. I don't think it's number 1 because down there we have some, issues on the numbering, but I'm under additional practice. Page 78 starts with a construction worker. Everybody there. So an object in free fall is moving under the acceleration due to gravity. Negative 9.81 meters per second squared. We're in the y-axis now. All those equations transform from x to y. Question 1. A construction worker accidentally drops a brick from a high scaffold. Don't be underneath it. What is the velocity of the brick after 4 seconds? So the things that we know on these questions is the acceleration of the gravity. Oops. They will hardly ever tell you this number because they assume you know this because you are in the vertical direction. So that's what we can write down as a given. We have a time of 4 seconds. Now, taking the equations on the right, we're trying to figure out a final velocity. So we know our initial velocity is 0 because he just drops the brick. He's holding it, drops it. So it's going to achieve a final speed, which we don't know. And we're trying to figure out. So which would be a good equation to use?
Could you say VF equals VI minus GT?
Excellent, Lala. Yes, that's perfect. That is exactly right. Yeah. So VF equals VI minus GT. Remember, it was VI plus AT in the x-axis. Now it's VI minus GT. Y-axis. This goes away because he's just dropping it. He's, I don't know, standing up here, and this distance is whatever it is. We can figure that out later. So it's dropping at a certain distance. Let's say it hits the ground. VI minus GT because the VI goes away. And now we just put in negative 9.8 times 4. And we can see that this is going to be units of meters per second, which is for velocity because, you know, you can calculate that. But just to write this out even more. The seconds goes away right there. And so we're left with meters per second. So that is a velocity, and it's negative because it's going down in the south, towards the south, downward. And that's roughly, what's that answer? Like 30 something?
39.2.
Cool, Sophia, thank you. Negative 39.2 meters per second. So when gravity is accelerating something 9.8 meters per second every second, that means after the first second, the speed is 9.8 meters per second. The second second is 19.6, and then 27.4, adding right, 39.2, 29, 30, 39.2, and so on and so on. So so the speed increases. It's getting faster every second. How much? By 9.8 meters per second every second. So just like we had the stipulation when the velocity is, no, it doesn't stop increasing. Absolutely good question. All questions are good. It doesn't stop increasing. Well, it stops increasing. It stops everything when it hits the ground, but it hits the ground at a particular speed. If you hit the ground at 0 speed, you wouldn't need a parachute coming out of a plane. So that's why you need a parachute, because without it, you're gonna hit the ground at a tremendous rate. And now we got impulse to consider. You're gonna hit the ground in a small fraction of time. You're gonna feel a maximum amount of force from the ground. That's a huge mass you're hitting, the earth, and it's over. So you need to use a parachute, and because the speed is not going to stop increasing. Yeah. So gravity is doing this, and your speed is getting larger and larger. They're in the same direction, so that's why this velocity here is going to get larger and larger. It's increasing. So if we would put this on a graph, we have a situation where, well, technically this would be an increase in the negative direction. If this was V versus T, this is going to do this. It's getting larger and larger and larger. through time, and that is going to be a negative slope or a negative acceleration, and that negative acceleration is going to be 9.81. So that's what's going on there. And then we can calculate how far it travels by taking the area underneath this. The distance that it travels is going to be negative because you're moving you're moving downward. So everything fits. Math fits the physics beautifully. That's why it's very important to be able to interpret data, graphs, interpolate data, reason from it. You can even create an equation from your VT graph that will predict the future. That's what equations do. Okay, so now let's go to letter C. I don't know why number 1 has BC. Maybe something else is letter A somewhere else. So like, and also if the ground was here and you're just dropping 2 meters, that's okay. But a plane is 300 meters up. You don't want to just have no protection. Okay, so how far does the brick fall? Which equation would be good for this one? Someone new. How far? Let's see. Anybody that hasn't? Pierre, what do you think? We have those 4 equations in the y-axis.
Yeah.
Okay, so which one of the 4 you think is going to be good to solve this question? How far does it fall?
I'm not sure, Mr. Kelly.
Anybody else want to help him out who's been here and seen the equations written up? We have 4 to choose from. All right, so we have 2 to choose. Well, 3.
Could we do the change in y equals half times the initial velocity plus final velocity, and then times the change of time?
Yeah, that works, sure. And what we'll find out with these equations, like both of those delta y equations, or all 3 of the delta y equations, will give you the same answer. They'll give you the same answer because the acceleration is the same for all. The thing that created those equations was the acceleration due to gravity, so to speak, just simply put. Since the acceleration of gravity is the same no matter what, and it created all those equations, then we'll get the same answer every time down. Now, I'm not going to go through the derivation of why that's true, or how gravity has created all those equations, but it has, and so therefore you get the same answer. If you use delta y 1/2 bi plus vf delta t, that'll be the same thing. You get the same number as your delta y bi t minus half gt squared. I don't know if I have time to prove that, but yeah, this should work. Okay, so this goes away. 1/2 b final delta t. B final we know already. It's negative 39.2. Put that in there and multiply by the time, which is 4 seconds. It took 4 seconds to travel whatever distance. Okay. Well, meters per second. So meters per second, and you can just do this so to make sure that your units come out right. If it's units of meters, that's good because you're trying to find a distance. So 39.2 divided by 2 times 4, negative 78.4. That's pretty far. Did we get that? So that is letter C there. Any questions? So yeah, it's pretty much like, let's just do one. Someone mute your mic there. All right, let's do the, like they say, number 4. Or at least in my book, or the next question. Suppose for the previous problem, you choose your coordinate system so that the opposite direction is positive, like when you throw something up into the air. So like, well, obviously, so like if you have a y versus t graph and you throw something in the air, it's going to come back down. Okay, so this direction would be, these are all the positive numbers. You're in the east or the north domain, so you're throwing your object up. So when it comes back down, it's going towards the south, yes, but still in the northern domain there. So we're going to take the perspective, as they say, with the opposite direction being positive. So what would the brick's velocity be after 4 seconds? Okay. So this is an application of what is in that section that we can just do right here interactively. I'll tell you right now, with a problem of this type, when the initial position and the final positions are the same, you have what's called symmetry. And that means when this is the same, when the positions are the same, like you throw a ball in the air and it comes back into your hand. The initial position, the starting point is the ending point. And so when that is the case, the uptime equals the downtime. Obviously, the distance will be the same because once you throw it, once it leaves your hand at whatever velocity it leaves at, it's not going to accelerate on its own and achieve something more just by itself. The upward velocity, the initial upward velocity is going to be equal to the negative downward velocity. So over here we have VI, and over here it comes back down at negative VF. Those will be equal. So we know that the downtime is going to be 4 seconds and it's equal to the uptime. And we can use that to calculate the distance that it travels upward. But getting to the point, let me move over here. So we have all those other things. So at the top, the maximum height, this velocity at the top will be equal to 0. So after 4 seconds, since it takes 4 seconds to go up as it takes 4 seconds to go down, that's our answer for letter E, or the first question. For me, it's letter E. So the velocity after 4 seconds, as we switch our directions, looking at things going upward, is equal to 0. Momentarily, though, only momentarily, because we have to imagine it now that when we throw a ball in the air, for just 1 instant, it's suspended, it stops. But then what happens is at that moment, simultaneously in that same moment, gravity is switching the direction of the velocity and it comes back down. So gravity is still going to be 9.8 no matter what you do, whether you go up or you come down, you go sideways. Gravity is gravity, gravity. So just in long story short, the velocity after 4 seconds, at 4 seconds, because it's at a maximum height, that velocity will be 0 at the maximum height. So every time there's a maximum height, anytime you have these free fall problems that say, well, the maximum height is such and such and such, what is the velocity at the maximum height? It's always 0. And another way you know that data analysis wise is that if you do a graph of y versus t, there's no slope here. What have we said about velocity relationship to displacement? The slope of a displacement time graph is the velocity. Slope is 0, velocity is 0 at the max. Math, that is your maximum point, your critical point. All the same thing. Any questions on that? So the answer is 0. There is no speed after 4 seconds at the top when we switch directions. How far does the brick fall during this time? What do you think it's going to be? After it achieves its maximum height and comes back down, how much distance does it? How far does it fall? Remember, gravity is still gravity. It takes 4 seconds to fall. Is that a trick? Think it's weird? Any rough guesses real quick? We got 2 minutes.
I'm guessing it's the same but different sign, or
It's the same distance, yes. Different sign because it's coming downward. But okay, we got 78.4 going down Y, and it's the same distance up. So there's great symmetry here. The distance up is the distance down, the time up is the time down. So the total time is 8 seconds if you were to, do the whole path. The velocity upward is equal to the negative velocity down. Why is that? Because gravity keeps basically everything in unity, ordered. Gravity has no respect of directions. It's going to operate the same way, whether up or down. Except that here, when gravity's operating, it's operating to slow you down, and then here it's acting to speed you up. Why? Because gravity now is going to be in the same direction as the velocity on the right-hand side, but opposite on the left-hand side. It's slowing down on the left. So that's why the ball slow, instantaneously 0 and comes back down fast. It comes back down at the same speed it started with. Symmetry, everything's symmetric. So, okay, that being said, okay, guys, I'll give it to 1 o'clock to turn this stuff in, get free quiz points, and you guys have a great Thanksgiving break. Great break. So get some rest and take care.
Bye, Mr. Kelly. Have a good break. Thank you.
Okay, thank you. See you.
thank you. Bye, Mr. Kelly.
Bye-bye.
Have a good break. Thank you.
Okay, you're welcome. Have a good one.
Mr. Kelly, I have a question.
Yes.
Okay, so I don't know if I can do it, but you know how on the college board, like AP Classroom, they have like at the end of every unit there's like there's a section for the like multiple choice and SAQs. Is it possible if you can unlock them, like for me to do them? Because I don't
Yeah.
know if you have access to that, like
I
because
do.
you do.
Yeah.
Because I'm not enrolled in the class, so I don't know.
Yeah, I haven't assigned it yet. Because the way that they have everything ordered over there is really bad. So I have to figure it's not user friendly. So I'll unlock it. Go.
Okay.
Mm-hmm.
Yeah, because I paid for the test, so I
Yeah.
might as well just take it and then
Yeah,
see how I
yeah.
if I don't do well.
And that's a good prep. I mean, those are excellent preps. So I'm gonna have everybody else prep over there. So I will open it up sometime this weekend at the latest.
Okay, thank you so much. It's a
Uh-huh.
very good help. Yeah, they have like very good like practices, and because we used to do it last year for AP Chem, and it was
Yeah.
helpful.
Yeah, no, it's amazing. They have the daily videos and all that stuff. It's
Yeah.
yeah. Really good.
Yep.
Okay.
Okay.
All right.
Thank you.
Yeah, you're welcome.
Have a nice weekend break. Happy
Okay.
Thanksgiving.
Yeah, you too.
Mr. Kelly,
Yeah. What's up?
do we have to do the Sukazi problem thing?
No, we're gonna skip that one.
Oh, okay. Bye.
All right, man. Have a good break and take it easy.
Mr. Kelly, hi. Can you explain on like what equations we should use for which like questions? Because I'm really confused on that.
Don't worry about being confused now. It's the first time seeing it. So all you have to do is worry about how to approach a problem. You have to
Mhm.
write down the given information first, and then like if you're with the free fall questions, you have 4 equations to choose from. So
Mhm.
it becomes a matter of practice. I never tell anybody this is what you use here. You have to work it.
So for example, like the x direction equations,
Yeah.
can I use any of them to get the answer?
Yes. Yeah. It just depends. Like if you're trying to get a displacement, there's like 3 equations to choose from, 3 of the 4, and it's just depending on what you have in the question. That's the best equation to use.
Oh, okay. So depending on what the question gives, there's okay.
Yeah.
Makes more sense. Makes more sense.
Mhm.
Thank you. Thank you.
All right. Sure.
Bye, Mr. Kelly. Happy
All right.
Thanksgiving.
Happy Thanksgiving. See ya.